On the air again. Our last attempt for this broadcast had multiple feedback loops in it, audio and video from somewhere. So we shut that down and started over, and we'll try it again. So again, this particular video conference and video presentation is an overview of our structural model development cost minimization processes. And what that really does is it encapsulates the context for the types of tools we've developed, the types of methods we've developed, and why we are focusing on these methods and tools and what their roles are. So large-scale system development is very expensive. It's a tremendous amount of information involved. And one of the primary driving factors for using these types of structural modeling tools and methods is cost minimization. Reduce the resources necessary to identify, create, and document an unknown or poorly defined system structure. So just as to start out on this, I'm going to bring up another document, which is a section of the preface to Structuring Complex Systems. It was 73, 74, which was written by John Warfield. And this is a very interesting section in that preface. And what he's talking about here is that if the full knowledge of basic structural models, so these basic structural models essentially are mathematical models, mathematical modeling approaches, to be brought to bear upon the development of interpretive structural models. Of course, the interpretive structural models are models of real-world business, social, technical systems. A significant advance can be made in the rational analysis and synthesis. So if we could actually take our knowledge of mathematical systems and somehow map them correctly onto our social technical systems, that would be a great advance. But again, it's impractical to expect those that are busily managing social technical systems to understand the mathematical components. And it's also unreasonable for the people that are mathematicians to understand the social technical components. And so there's this dilemma of how do you actually bring these tools to bear? And even if you could bring the tools to bear, then how would you actually perform the mathematical work? And so I believe there's been some advances made in this area of applying these structural modeling techniques over the last 40 or so years. However, there has been great advance in our computing systems. And so the extreme tyranny of working systematically, basically, that is going to be handed off to the computer. So essentially, we still have the same types of problems we had back in the late 60s and early 70s as far as dealing with large-scale complex systems. So the components of structural modeling have been divided into essentially three parts. And the basic structural modeling and the interpretive structural modeling were developed by Warfield. The structural integration modeling component was developed by Systems Concepts, and essentially that's used to be an area where the mapping of this knowledge between the basic structural models and the knowledge and the empirical data from the social technical systems are analyzed. So as you can see here, we have the basic structural model basic structural modeling area, which is the area of mathematicians and have mathematical knowledge. The interpretive structural modeling, which is essentially the areas that are the day-to-day social technical systems managers, people that manage large government and business and social systems. And you need to place those in proper correspondence. And so we use computers actually to do the work to place these in proper correspondence. So we named this area structural integration modeling, where the goal here in structural integration modeling is to properly align the resources from the basic structural modeling and to the problems that we find in an interpretive structural modeling arena. And this is an interesting area, and it has some unique aspects. And we've developed some tools to actually help us in the structural integration modeling area. And one of those tools is an abstract relation type concept that's used to provide a form, a specific standard form for encoding information. And then the augmented model exchange isomorphism that we've developed for use in this area as a map, as a conceptual map of what can happen and how we can actually map things between these two areas. And so we'll talk about that a little more as we go forward here. But these are the general areas, and one of the driving values in the structural integration modeling activity is cost minimization and cost reduction. So what we want to do is we want to effectively use our mathematical knowledge to solve the problems of social technical systems. So that is a major driver in what we do in these specific areas in the structural integration model. We'll now take a look at a little bit more detail at the aspects associated with complexity reduction. Let's talk just a little bit about what we want to do and how we are able, what techniques we can use to reduce complexity. So, bring up this other screen here. So complexity reduction is extremely important in large-scale social technical systems because they have a tendency to be perceived as being very complex. And one of the reasons for structural modeling, and one of the reasons for imposing structure on these systems, is to actually reduce this impression or to reduce this feeling of complexity by imposing order. So essentially structural modeling is we're modeling the structure in order that's not apparent at the surface, but what's underneath and what actually is going on within the systems. Imposing that type of structure then allows us to develop rules and to greatly reduce uncertainty and to greatly reduce the amount of effort it takes to understand how the system is operating. Second aspect of reducing complexity is to focus on a single system aspect or organizing relationship at a time. So if you need to actually look at 2 or 3 or 4 aspects of the system, then your approach should be to take each single system aspect or organizing relationship, create a model for that, and then integrate those models in a way that meets your goals. So reduce complexity by reducing uncertainty and then you focus on a single system aspect, that also reduces uncertainty because you know exactly what you're looking at. And then when you have more than one organizing relationship, as you integrate those or as you aggregate them or you work with them, that again reduces uncertainty because you are able to look at and name and understand how you're putting these things together, how the second order type of relationships going on. Of course, you use two types of languages, and natural language, which is informal, which is in the ISM area, and mathematics, which is a formal language, which comes from the DSM area. And then you employ two structured interfaces. So the natural language interface to mathematics and the mathematics to system description. These two interfaces live in the structural integration modeling area. So we start bringing things together from the informal type of language area and the formal type of language area, and we start working with them in the structural integration modeling area. Like I said previously, there's a number of tools that we've developed to work with and understand, that help start understanding these things better. And one of those is the model exchange isomorphism. And what we'll do now is we'll talk a little bit about what that model exchange isomorphism is and why it's important. So here we go. So the augmented model exchange isomorphism is basically focused on the mapping or the isomorphic transforms between three language types. And those three language types are prose, structured graphics, and mathematics. And so in this particular slide, what we're looking at is the prose expression of primary logical concepts. And we've taken these three primary logical concepts, and we've broken them into three subgroups, which we believe covers the complete range of logical interactions. There may be logical interactions specifically outside of these areas, but by mapping the 27 groupings that we've done, we will be able to say what's inside and outside and then what's inside each one of the 27 buckets. So starting to map this area and take, for example, symmetry. So if something is symmetric, then we know it is not asymmetric and it's not non-symmetric. So once we know what one of these characteristics and properties exist, then we know that the others don't. So there's a logical relationship and a logic about the mapping of these logical properties to the relation. If something is reflexive, then we know it's not irreflexive and it's not non-reflexive. The same with transitive. If we have a transitive relation, then we know it's not intransitive and not non-transitive. This is a basic type of reasoning and logic that we're thinking about here. One of the reasons that we chose to use all three of these logical properties as a group, you'll see here, see if I can make this, get the whole slide set. Yeah, right here we go. Okay. The reason we decided to use the three properties of the group is basically an artifact of the job that it really needs to do. So when we look at we're mapping the mathematical area, mathematical logic area, we're mapping that to the human natural language area. And when we look at the way logic is addressed in mathematics, there's a number of different approaches, but basically there are specific names that are associated with groups of 2 or more primary logical properties. And so we would have, let's say, for example, an ordering property or a equivalence property. Equivalence property is symmetric, it's reflexive, and it's transitive. So we have groupings that are put together, or we have partial equivalence. And so, or a pre-order, or things like that from the mathematical arena, which really are names that are used for different combinations of logical properties. So when we look at the natural language, social technical area, we look at the way that rhetoric and grammar and logic is used in those areas. We see that there's mostly a focus on one type of property at a time. Rarely do you get two, and they're not really named. They're just kind of in the argument, and they really don't have specific names for those types of arguments. Some of them do, but mostly in everyday logic, everyday social technical, and of course, you don't go to that level of formality. So to be able to address the two sources of information and the way that this information is naturally handled in these two areas, we decided that we needed to use all 3 properties, create 27 groups, and eliminate the uncertainty associated with those, with all the groups that are essentially included. And this creates a map that we can now take information either from the ISM arena or from the BSM arena, and we can map it onto these specific areas. So one of the comments that we got on our last month's video conference is that some of these buckets in the 27 are mathematically, logically invalid, which is a very important concept, because if you find combinations of these logical properties that are invalid, then those are ones, if you find them expressed in natural language, you wouldn't want to use those natural language expressions, try to map them to logic or to mathematics, because it would be very difficult, if not impossible. From a systems standpoint, also we looked at the way that these primary logical properties are applied. Of course, reflectivity involves just one individual, and symmetry involves 2 individuals, and transitivity involves 3 or more individuals. So from a systems focus, we decided that really the most important logical property, the system structuring property that was important, was symmetry. For the simple fact that you need 2 or more individuals for a system. Reflectivity only involves 1 individual, and transitivity involves 3 individuals, but 2 at a time. So you really need to have a type of symmetric relationship underneath the transitive relation. That's a very non-specific idea, but you can't have 3 things related without having 2 things related. So symmetry is the logical property that was picked. Then we went through and created permutations of these relation properties that are necessary to map this whole logical territory, these logical concepts. Okay. And this specific aspect here is an important idea to understand, so that after we choose symmetry as our guiding structuring property, we then find that asymmetry creates the hierarchy. Symmetric types of property, a symmetric property creates a network, and then non-symmetric creates a combined network and hierarchy. So these are essentially important structures, because what I found so far, and I think other people have found, is that essentially the hierarchy, the tools and the logical concepts and the mathematical methods that you would use in the hierarchy, which are logical rules and other types of lattice structure and matrix approaches here for binary logic, what we find is these tools that are used in the hierarchy area are significantly different than the types of tools that we will use in our network areas. So in the network areas, we'll analyze for highest value configuration, filter out controlling structures, analyze the structures. And in this particular approach, we'll use evolutionary algorithms, intelligent agents, a number of other types of artificial intelligence types of approaches we would use to analyze networks, which are significantly different tool sets than we would use here in the hierarchy. In the combined hierarchy and network area, where it's non-symmetric, the tools that are used here essentially partition this combined hierarchy network into its hierarchical component and its network component. It's a technique that's developed by Warfield, and it was published in one of his publications in I think the early 70s. But essentially what you do is you have a process where these network nodes this whole group is reduced to one node. You take this and you reduce it to one node, and then you have a hierarchy. So when we're thinking about whether or not you can have an asymmetric and a reflexive type of logical property together, well, or what types of logical properties match each other, we have some interesting situations in non-symmetric approaches because we have them both. So if we apply our tools here and create a hierarchy, we're going to have one set of rules. Or if we pull the network components out and analyze them by themselves, we're going to have a different set of rules. And in this particular case, the natural language relationship or the mathematical relationship that generated this structure may have some interesting logical properties which are not valid in the hierarchy analysis or valid in the network analysis. And as Janet pointed out, in the 1973 paper that Warfield wrote on binary structuring, we had some comments about this, which I think are very appropriate and apply directly to what we are discussing. As soon as I can find the paper, I will bring it up, and then we can go forward from there. There it is. All right, I found it. All right. So this is a copy of the paper that Warfield wrote and published, 73 Binary Matrices and System Modeling. You'll notice here that this is connected, and it's not a directed graph. It just is non-directional, just a general graph. But then figure 2, directions. It's a directed graph. And there's some comments about the reflexive himself, referential loops in figure 2. And essentially what it says, in figure 2, it appears irrelevant where the arrows are added on the loops at vertices. But the question arises, for example, why would you have one or not the other? In many instances, the relation R is of such nature and the system analysis is conditioned such that it does not matter whether you show this reflexive relationship. The convenience can be the deciding factor. So there's some issues there on these types of analysis that really are important, but how do you break those out and what do they mean? Well, we can see here in figure 4 where we have a type of graph that has a matrix partition, and this particular fundamental graph is then transformed into this hierarchical display, which is a directed asymmetric graph. And these are this technique then really changes the logical structure by condensing these forms, these networks, into a single node. And then when that happens, then you can represent these in different ways and different formats. But what we have now is a partition then, which we have, see where we have 1, 2, and 3 is right here. This group is in a network. And then we have 5, and then 4, and then 2 and 3 here. So this particular set then was displayed in this manner. So when we're translating from, back to the MEI section here. So there are techniques, as we've seen, to create hierarchies from combined hierarchies and networks. We also have techniques to analyze a network. And, well, why is this important and what does it mean? And I think that when we're bringing natural language relationships and natural language into proper correspondence with the mathematics, we can see here that from a mathematical point of view, we're actually really going through in the sim area and changing these fundamental logical property structures. And so how do we change those? What's are valid? What are useful? And so I think that what we've found so far in the analysis of the situation is that we find some of these combinations and some of these permutation groups, some of them are more valuable or more easily handled in mathematical tools than others. And so one of the ones that's very, it's turned out to be very useful is, let's see, asymmetric. Yes, it's asymmetric, irreflexive, and transitive right here, number 221. So in this particular area, you look at this and say we have an irreflexive, asymmetric, and transitive relation. And these then have properties of logic and have properties of for analysis that are very good for predicting other answers. And so let's say irreflexive, we use a north of example. City A is not north of itself, so it's irreflexive. Asymmetric, so city A, if city A is north of city B, then city B is not north of city A, so it's asymmetric. And of course, transitive. City A is north of city B, city B is north of city C, then city C is north of city A. So these are very fundamental. This group right here, AIT221, IAT, irreflexive, asymmetric, and transitive, has some excellent logical properties. We show in the first strict ordering approach with the 19 cities problem, we show the way that you can efficiently use the logic to reduce the number of data points you have to get empirically. So remember what we're doing here is we're using math to help us reduce the cost of creating the system structure. So we could create the system structure simply by asking every question, if you had enough time and resources. The systems get very large, the permutations explode, and that option just doesn't really stay viable for a system of any size. So we need to have some techniques that we can use that help us infer the answers given a base of empirical data. And then the other component is also feedback from that. So if we have data that we've taken, we have empirical data, we have a relationship, and then we've inferred information based on the relationship, then also what we want to be able to do is understand enough about how that structure is developing to then, when we go sample the system again, use the information we have to sample and get the highest value next data point. So when we actually go and get some data, we're not just randomly selecting data. Now what we're doing is we're guiding our data collection, and we are improving the cost benefit that we will get back. So what we'll really want to do after we get the model started using this type of approach is to then sample the part of the system that we believe will give us the highest logical payoff. So within this mapping of the properties, there may well be things that are mathematically improbable, let's put it that way. So that, or difficult or impossible to calculate because these concepts don't make much sense when they're put together that way. The idea is to mark those. We have a map here of these 27. The idea is to use these buckets to put our information in. I think that irreflexive, asymmetric, and transitive, we talk about this relationship, it is very, it's very powerful, and it has very good qualities for developing system structure. Now, if we go irreflexive, symmetric, right? Well, irreflexive, symmetric, and transitive, then that's what we looked at in the cities problem, where we allowed more than one city in each level. And so now in this particular case, what happens is we now need to ask and gather more empirical data, because in an asymmetric situation, if we know that city A is north of city B, we can infer that city B is not north of city A, and they're not at the same level, because we don't allow that. So symmetric case, that is not the Yeah, in the symmetric area, when you do irreflexive, symmetric, and transitive, then that's not the case. So we have to ask and say, okay, if city A is not north of city B, then we have to ask, are they at the same level? So that kind of at least doubles the amount of empirical information you need to collect. This is an area that is interesting in working on figuring out some strategies for reducing the amount of empirical data that needs to be collected and looking at some other components. So in any case, these are some of the things that are starting to, some of the information that's starting to be developed, some of the information that we can add once we have these specific types of groupings of primary logical relations. So we started, and of course, I think what you can notice that there's no anti-symmetric type of logical relationships here. We don't allow anti-symmetry in this table. And so we can actually have the equivalence component to anti-symmetry, which is reflexive, symmetric, and transitive, which is 1, 1, 1 up here. It's the equivalence. That's that part. Or the asymmetric piece, right? The asymmetric piece that runs through here is very strong component of the anti-symmetric, but you need to, it's either going to be one or the other. You need to have empirical data, you have to have some knowledge about your system to determine whether or not within the anti-symmetric component it's going to be equivalent or it's going to be asymmetric. And an asymmetric relation is also anti-symmetric in some definitions. So there's a mismatching of naming, there's an overlapping, there's confusion about that. So what we've done is we don't allow anti-symmetry. There may be some cases we find in the future that will expand this and allow it, but right now we believe we can handle all of the anti-symmetric types of example cases using these basic combinations. So let's look at, so are there any questions, Mary? I don't think you have your microphone on. All right.
I didn't have my microphone on.
Yes.
No, I don't have any particular questions at this point in time. Thanks. I'm busy taking notes here.
Okay, all right. So far it's, all right. So let's start looking at the hierarchy of mathematical theories. We looked at this one a while back, talked about it a little bit. There's an interesting arrangement, in my mind, from a number of different points. And the area that this was developed from, of course, was the area of theoretical computer science, where they're looking at ontologies, and ontologies and how you process certain types of natural language concepts, and interoperability. How do these systems interoperate with each other? In this particular hierarchy, is arranged so that the theories here at the top have fewer axioms than the theories at the bottom. So, okay, so this means that relation has fewer axioms than an irreflexive relation and an anti-symmetrical relation. So as we go down the chart, we have more and more axioms. But it doesn't really say what kind of axioms, how they relate to each other. There's just more of them. So what we did was we took a look at this, decided to look at it and arrange it into a included in. See if we could take the components that we're interested in and put those into an included in hierarchy that addresses some of the issues that we've been talking about here. So let's see if I can find that one. Here we go. So we have the general included in hierarchy. There we go. And we can see that we've arranged this to where we have what we call the primitives at the bottom. And the primitives are basically symmetric, asymmetric, irreflexive, reflexive, transitive, and intransitive. These have no other logical properties that basically come into them or are necessary. These are the basic primitive blocks. And then what we did, of course, in the augmented model exchange isomorphism is we added the concept of non-symmetric, and then non-reflexive, and non-transitive. And so these now need two specific primitives to support them. So non-transitive has to have an intransitive component and has to have a transitive component. Of course, the same with non-reflexive. It has to be reflexive and irreflexive, and non-symmetric, symmetric, and asymmetric. The other identification of two inputs we've found in the literature is similarity, which is symmetric and reflexive, partial equivalence, which is symmetric and transitive, and preorder, which is reflexive and transitive. Then we find that the logical groupings then that have three fundamental components in them are equivalence, strict order, and strict total order. And then anti-symmetric has a grouping of three equivalents, but then it steps down and brings a primitive back up, which is asymmetric. And then anti-symmetric goes into partial order. So this is basically an included in type of hierarchy for these math theory. But what we wanted to do is we want to look at this a little bit more specifically about the, think about what this included in relationship really meant. So we did a more detailed approach here with a specific type of mathematical theories approach. And essentially here, then, it's what we've said is that this arrow must be included in, whereas the dotted arrow, dotted line, it may be included in. So all the ones that the primitive runs into the second level, those are all must be included in. Third level, it's all must be included in. But when we get to where we have the fourth level here, these are may be included in. So that an anti-symmetric relation may be included in, but they could all be equivalents. Equivalents could be included in, but they could all be asymmetric. And the way that you would find out the difference from this, again, is empirical data in our case. So, because that's what we're doing fundamentally with the logical principles down here, is looking at, okay, we're taking, gathering empirical data, using this specific logical relationship to infer other information. So it doesn't seem reasonable to use a type of logical property that needs you then to further gather more logical or empirical data. Because we already know if when we're going into the analysis that we have a symmetric or an asymmetric type of property. And so using the concept that all asymmetric relations are also anti-symmetric, that creates uncertainty. And so you can say that, and in context you eliminate the equivalence piece, and this allows for some confusion. So what we've done, we've essentially said, no, we're going to, at this time, not use anti-symmetric or the partial order. We're going to look at these and use these in a different way. And we basically use different techniques to achieve the same outcome that you would get if you used anti-symmetry or partial order. So that's one of the key things that we're working on right now. And it's very interesting. Essentially, what it boils down to is here where we have equivalence, and we have order. And the idea is to, step one, create equivalence classes. Just go through and gather your information and find out whether or not these things are equivalent. That can be fairly efficiently done depending upon the system structure. And then once you have identified your equivalence classes, then of course, then you can order the equivalence classes. The equivalent, this approach has some advantages because essentially it says nothing about the total set. When we get up to a partial order is a partial ordered set. And so that when we get to that level, we say, okay, we have to have unique elements throughout the set. That's the definition of the set. But with this particular approach, in our equivalence classes, if our equivalence classes are set, then we can look at hierarchies, we can look at other system structures that actually have that have one element actually displaying that exists in multiple equivalence classes. And this opens it up a little bit. Len Conkell talked a little bit about some of the areas that they've discovered where the hierarchies would allow this type of, that the hierarchies actually need this type of flexibility. And I think one of the examples he said was organizational chart where you have one person that plays multiple roles. Well, that one person basically then would be, let's say, in a VP, and let's say it was in a VP slot, and then the other person is also, let's say, the chief security officer. That's basically reports to the VP slot. Say the VP has basically just been promoted from that slot. They haven't hired anybody in yet. And so he's playing both roles. And so in this particular case, using the equivalence classes allows that type of system representation. So you can have one element that appears in multiple equivalence classes because each equivalence class is going to be treated as a set. And then the set of equivalence classes then, of course, will be treated as a set and those will be ordered. Kind of gives us a much more flexibility in the types of systems structure we could model as opposed to partial order. These are the things that we're working on right now. The plan, of course, is to have a read-ahead out for this particular video, but events overcame the completion of that document. So the new plan, the replan, is that we're going to have a document out that collects this information and distribute it to the list. The what we'd like to do is, again, continue this discussion. And it's an excellent discussion on how systems engineers and systems scientists can start using the information that we have to create tools that cost effectively identify the structure of a very large system. These are areas of great interest to many people. And my slide just went off of the chart here, so I'll see if I can bring the slide back up. And we'll go over here and look at this. So again, going back and look at this particular part again. So the organizing system structure pieces that we have within the 27 buckets, the ones highlighted in green here were the areas and the properties that Warfield addressed. So we can see that there are many other combinations that are present on this chart, which are there or for completeness and to reduce uncertainty. So once we are taking the information from the mathematical side and starting to map that to the natural language side, this complete map or topology of these permutations is necessary to be able to just keep track of the bookkeeping. So as we talked about, we said the irreflexive, symmetric, and transitive, that's very efficient, very powerful type of logical inference here for hierarchy. Well, I mean, not the asymmetric, excuse me, the reflexive, asymmetric. Irreflexive, asymmetric, and transitive. That was it. Irreflexive, asymmetric, and transitive. This one is very powerful. These others have other types of properties, but in our symmetric ones, we need to really use different types of tools than we do in the asymmetric ones. And that's another reason to not use an anti-symmetric concept, which actually allows both in the same type of construct. It's quite confusing. We're coming up to the end of this particular video. And if there's any questions, you can address them to the list. And we will have this document out within the next week or so. It's final type of summary here, if we can bring up. Here we go, looking for the chart. One more chart, come on. Where'd that chart go? Here it is. So essentially what we're doing is we are looking down here in this area of the structural integration modeling. So where the ART and the AMEI are. We're bringing in from this interface from the math area into the structural integration modeling. We're bringing in information from the interpretive structural models, which essentially seems to be disconnected in many cases. And we developed the AMEI and the ART to help map and communicate this information and to communicate information about solution approaches that seem to be valuable. So with that, I'm going to sign off. Any specific things I should address, you think, Mary, before we sign off here?
Oh, I don't think that there's anything else that I can think of. However, it was extremely interesting going through this last set of material that we've developed to recognize how actual natural language relationships don't necessarily map really easily or directly to a mathematical construct, and vice versa. That you can take something in mathematics and try to map it directly back to a natural language relationship, and it just hangs up at certain points. And so I think that this is for me, has been an extremely valuable exercise.
Well, hopefully that that was kind of the message, and that's kind of the idea to express and provide the context to folks of what these tools are for. And it's really exciting. I'm glad that people are asking these types of very good questions, and we'll have hopefully more input, and we'll help create and add to this as we go forward. I have some software under development with Thomas, and I'm just looking forward to making more progress. With that, I will sign off this broadcast.